Okay. So, today we're going to look at some calculus. All right. So you'll want a piece of paper out or something like that. We're going to briefly dip our toes in today into calculus. We won't go too far, but then later on, toward the end of this class, we'll probably go more in depth into this stuff. Okay, so please forgive me for just kind of like teasing you a little bit with the calculus, but then taking it right away kind of thing. But we are going to, we got some other stuff we got to cover first, right? But I wanted to because we're here. We're at the point where we can do it, so let's just do it. All right. So what we're going to look at is, or try to understand, is the slope of a function. Okay, and you already kind of have an understanding of the slope of a function. For example, if we consider f of x equal to 2x plus 1. Okay, there's a function, right? And without even having to think too hard, hopefully, what is the slope of this function? 2, right? Because it is a what? It's a linear equation, or linear function, right? And the slope is 2, okay? Did you need Lindsay? Yep, she's here. She's doing great, so thank you. All right, so yeah, the slope here is 2, okay? Or as a fraction, 2 over 1. Okay? So, we already have an understanding of what the slope of a function is like, right? The slope here is 2, or 2 over 1. All right. If we graph it, all right, let's see here. So, the y-intercept is at 1. I'll go up 1, 2, and then right 1. So there's another point. I'm not going to bother doing any more points than that. You get the idea. Okay, it looks something like that. There's our line. Okay. And the thing about a line, right, if you remember back when you first learned how to find the slopes of a line and stuff like that, you can take any 2 points on your line, find the slope between those 2 points, and that is the slope of your line, right? Any 2 points on your line, find the slope between them, that's the slope of your line. Any point on your line, right? Any place here, the slope is going to be 2. All along this line, the slope is 2. Okay? Constant slope there. Okay. The positive 2, by the way, the positive 2 in the slope indicates that the line is what? What kind of behavior do we see here? Since we have a positive slope, that indicates that this line is what? Increasing, right? And if we have a negative slope, we expect the line to be what? Decreasing. And if we have a 0 slope, not positive, not negative, 0, what would we expect for that? Constant, right? Okay, so keep that in mind. So that's our basic understanding of what we know about the slope of a function. But now let's consider a different kind of function. For example, we'll say, I don't know, f of x, I'll use f of x again, equal to negative 4, negative x squared plus 4 is what I meant there. Sorry. Negative x squared plus 4. Okay? So, what will the graph of this look like? It's a parabola, okay, right? And what kind of shift do we have here? What kind of transformations do we see? So for, not to the left, nope. For up. We're going to go for up, okay? And remember, if the number is inside with the x, and then the quantity is being squared, that indicates left or right. Since it's on the outside here, that's going to shift things up or down for, in this case, up for. And the negative x squared is going to take our normal kind of like U kind of shape, and it'll make a frowny face kind of shape, right? So I'll just shift it up 4, so 1, 2, 3, 4, like that. And that means we're going to also have zeros here at negative 2 and positive 2. And vertex is at positive 4, and so I'll kind of like sketch that parabola right there. Okay. So now, what's the slope of this function? What is the slope of this function? Okay. Well, that's kind of a weird question to ask maybe for this kind of problem. Right here, for the line, it's no problem to ask that. The slope of a line, it's 2, right? We can see it. We can also count the slope here, right? How much it rises and runs by. But here for this, the slope is a little bit trickier, right? First of all, is the slope going to be just a single number here? No, it's not. Okay, the slope is changing. Okay, so maybe we won't be able to identify what the exact slope is because the slope is changing. Okay, the slopes are changing, but I bet you all have an intuitive, or some of you at least, have an intuitive sense about what value the slope will be. So for example, if I were to pick a point like right here, okay, and say, what would be the slope at this location? Well, maybe you can't give me a value, but you can, I bet, tell me whether it's going to be positive, negative, 0, or, well, I mean, maybe you're not sure. So it's going to be positive. Why would we think the slope here is going to be positive?
Well, which way are you going?
It doesn't matter which way I'm going, actually.
So positive since you're going to go up.
Because this is, what behavior do we witness right here? It's increasing. It's increasing, and so we expect here this slope to be positive, okay? So exactly right. The slope here will be positive. Okay. What about the slope at the point like right here? Negative because why? The function is decreasing kind of on that interval there. Yeah, so we'd expect to have a negative slope. What about the slope right here at the point here? What do we expect this to be? Constant, which means slope of what? Exactly 0, right? So here we can even give the exact value. It's a 0 slope. Okay. By the way, what other special kind of point is this? It's the vertex, but what else can we call this? Y-intercept. What else? A maximum. Absolute maximum, or even a relative maximum if you like. Yeah, okay. So the place here, notice our slope is 0 here, and that also locates, excuse me, our relative maximum. Okay, or an absolute maximum in that case too. Okay, and in fact, later in calculus, you'll learn there's a theorem that if there is a relative maximum or if there is a relative minimum at a point, then the slope will be 0 at that 0 or undefined at that location. Okay. So, no surprises there, maybe. Okay, but our slope is changing. Slopes are changing depending on where we are on the graph, right? It depends on our location. Bless you. Depending on location on the graph. Okay, that's a bit of a new kind of behavior than what we talked about here. Anywhere we are on the line, the slope's always 2. But here, depending on where we are, sometimes we're going to have positive slopes. Sometimes we're going to have negative slopes. Sometimes we'll have a slope of exactly 0 at a single point. And that's another kind of weird thing that we're talking about too, right? I'm talking about finding the slope at a single point, right? Finding the slope at a single point, because these slopes that I'm referring to, they are tangent slopes. Tangent slopes. So what I mean by tangent slopes is, if you remember back from geometry, you talked about tangent lines in geometry. You'd have a circle, right? And a tangent line would intersect your circle at exactly a single point, right? One point, tangent line. So we're talking about tangent lines to our curve now that will intersect our curve in the nearby locality there, or nearby location at exactly a single point. Okay? So you can imagine, if you kind of were to picture this, the slope here looks something like this, right? Here, the slope here will look something like this for a tangent slope. And here you could pick something like, something like that. Okay, that one didn't work out so nice, but you get the idea there. Okay, so you can kind of see those slopes, tangent slopes. Okay? So that's great, but can we be more precise, right? So the real question is then, how do we find the slope of a function at a single point. Right? We know how to find the slope of a function given 2 points, right? You just use the slope formula, rise over run. But how do you find the slope of a function at a single point? How can you find the slope just using 1 point? The answer to that is with calculus and using the derivative. Something called the derivative. Okay? We use the derivative to find the slope of a curve. Okay? So, I'm not going to focus later. Later, I will spend the time with you guys to help you kind of see how we actually develop the idea of the derivative, like where it comes from. It actually comes from the slope formula, okay? And we use limits combined with the slope formula to create this idea of the derivative. So for right now, I'm just going to show you the calculation that we do to perform the derivative, the limit definition of the derivative, and later I'll show you kind of where that comes from. Okay? So first of all, to denote the derivative, to show that we're talking about the derivative, we're going to take f of x. Okay, but we want to talk about the derivative of f of x, so we're going to put an apostrophe right there between the f and the parenthesis. You read that as f prime of x. F prime of x. Okay, f prime. The prime stands for the first derivative there. Okay, and the way we find the derivative of a function f, which is f prime of x, we take the limit as h approaches 0 of f of x plus h minus f of x all over h. It's our old friend, the difference quotient, but now with a limit in front of it. Okay. Now, if we try and evaluate this difference quotient right away by doing a direct substitution, what will we end up with? Not just something over 0. It'll be, undefined. So we'll have a 0 in the denominator, but what are we going to have in the numerator? Imagine plugging a 0 in here. What's x plus 0? X. F of x minus f of x is what? 0, and we'll have over 0. So this indeterminate form if you try a direct substitution right off the bat. But of course, oftentimes we can simplify something, then plug in the 0 so that it's no longer an indeterminate form. Okay? So direct substitution right away will result in 0 over 0, but we will be able to simplify it. So let's actually then apply the derivative. Let's find the derivative of one of our functions. And let's go back to our first function here. Okay? Now, we already know the answer to this, right? If the derivative describes the slope of the function, what should be the derivative of this function? Better be 2, right? The slope of our function, we already know it's going to be 2, right, from just algebra. So we better, if we do the limit definition of the derivative to this, we better get just 2 as our final answer. So let's see here. We'll take the limit as h approaches 0 of f of x plus h minus f of x all over h. Excuse me. Okay, so I'm just writing the definition of the derivative, and now I'm going to actually substitute in. So we're going to find the derivative of f of x equals 2x plus 1. Okay, so we're going to do that here. Okay, so limit as h approaches 0. So f of x, right, is equal to 2x plus 1. So f of x plus h then is going to be 2 times the quantity x plus h plus 1. Okay, right? If f applied to x is 2 times that x plus 1, f then applied to x plus h is 2 times that x plus h plus 1. And so I'm going to get here 2 parentheses x plus h plus 1 minus then f of x, which is the quantity 2x plus 1. All over h. Okay, I know it gets a little confusing because you have x's and h's mixed together and stuff like that, and you're not really sure, you know, it can get a little bit much, but I mean, this is how we do the limit definition here. Okay, so just try and keep those x's and h's straight. All right. What can we do to simplify this expression here, I guess. What can we do to simplify? What will be a good next step? Distribute the 2. Also distribute the minus sign as well, right? So I'll go ahead and do both of those. Distribute the 2, so we get 2x plus 2h plus 1. And then distribute the minus, so minus 2x minus 1 all over h. Okay, that definitely looks messier, but there's stuff that cancels out, right? What simplifies here? What can we cancel? 2x and minus 2x. 1 and negative 1. And so that's all that's left in the numerator to cancel out. So let me rewrite here a little bit. We have the 2h still left in the numerator. We have the h still left in the denominator. If I try and do a direct substitution now, I'll still end up with 0 over 0. But there's still a simplification we do here. What's 2h divided by h? It's 2. And what is the limit as h approaches 0 of 2? 2. Okay. Now this is not mind-blowing, right? We could go to Algebra 1 classroom, ask the same question, maybe we'll come to the same answer, right? It's not impressive. But you can see at least the calculus works, right? It does what it's supposed to do, right? It answers what we know should be the answer there. So like, okay, so maybe this thing will allow us to be able to find the slope for something whose slope we don't know right off the bat, right? The slope of like a quadratic function. Okay, so we're going to do that next. Before I do that though, any questions on this? Any questions on this? Okay. So again, the derivative we get here, this you could also alternatively say here, you know, f of x equal to 2x plus 1, f prime of x then is equal to just 2. Okay, taking the derivative there, we get f prime of x equals 2. Questions on any of that? All right, so now let's take the derivative of something more interesting, right? Something whose derivative we don't already know. Something that, you know, Algebra 1 students couldn't do. Or wouldn't know off the bat. All right, so then let's find the derivative. Find f prime of x if f of x equals negative x squared plus 4. Okay. So we're going to again use the limit definition here. So the limit as h approaches 0 of f of x plus h minus f of x all over h. That first piece, right, that first substitution, remember, is the hardest thing. We've got to figure out what f of x plus h is. So if f of x is negative x squared plus 4, f of x plus h then is going to be negative x plus h quantity squared plus 4, like that. Okay, so I'm kind of like writing it over here to the side to see it, and now I'll just rewrite here. So it'll be the limit as h approaches 0 of negative quantity x plus h squared plus 4 minus, and then f of x quantity negative x squared plus 4 all over h. Okay. So far so good. Any questions on any of this? Okay, now the simplification here is a little bit trickier. Right? A little bit trickier. We have to square the quantity x plus h. Okay, so negative x plus h quantity squared. So it's going to be, you know, if you think about it here, that really means, you know, x plus h times x plus h, right? That's what that means, right? X plus h times x plus h. So we're going to get x squared plus 2xh plus h squared plus the 4. And I'll go ahead and distribute the minus sign. So it'll become minus and negative, so plus x squared minus 4 all over h. Okay. And again, I'm writing out a lot of the steps here just so that way everyone can follow along. I know it's a lot of writing. All right. This is fundamental to, you know, a large portion of our calculus that you'll be doing next year if you decide to take calculus, either AB or ABBC. Okay. But the good news is you won't be doing this for forever, you're going to be figuring out shortcuts and stuff like that. Okay, so you won't be doing this for forever, but you should. This is something you're going to need to be able to recognize in any way. So, all right, I'll distribute the minus sign here, so we really end up with negative x squared minus 2xh minus h squared. And we have the plus 4, the plus x squared, and the minus 4 all over h. Okay, so does anything cancel? The 4s do. See you later, 4s. What else? X squareds. Anything else? No. All right, but what's left in the numerator? We have, well, I'll go ahead and write out one more step here. Negative 2xh minus h squared all over h. All right. Can this be simplified any further? So, yeah.
Allow h and then divide by it.
Very good, Andrew. Exactly right. Okay, so we don't want to just cancel the h's out like this, right? We don't want to just like cross out the h's because this has got subtraction in here. So instead we need to do exactly what Andrew said. We're going to factor an h out of the numerator, and then we can cancel because it's now multiplication with that factoring. So it'll be h times negative 2x minus h all over h. The h's cancel. Now they cancel, right? And so we have limit as h approaches 0 of negative 2x minus h. And now what can we finally do? Last step here to evaluate this limit. Substitute, direct substitution. 0 goes in for h, we end up with negative 2x. And that's the derivative. All that work. Okay, so f of x is equal to negative x squared plus 4. F prime of x is negative 2x. Okay. Now, what does this even mean? There's an x in there now, right? When we found the derivative earlier for the line, the derivative was just a number, 2. Well, let's think about this. On a line, no matter where you are on the line, what's the slope? No matter where you are on the line, what is the slope of that line? Well, in this case, no matter where we were on our line, what's the slope of the line? 2, right? Our line was 2x plus 1. That's the equation. Our slope was always going to be 2. But then we discussed for the parabola, your slope is going to change depending on where you are on the curve. So, for example, here, okay, and by the way, what's the x value here? The x value here. Y value is 0. Negative 2. Yeah, negative 2. So let's think here. We said there was going to be a positive slope when x is equal to negative 2. When x is equal to negative 2, what's our slope going to be? Positive 4. The slope at this point is positive 4. Positive 4. Okay? What's the slope going to be here? Well, what's the x value here? 2. Negative 2 times 2, negative 4. It's symmetric even, right? The slope here is positive 4, the slope here is negative 4. All right? We said here the slope was going to be 0, right? We kind of eyeballed that and said it was going to be 0. What's the x-coordinate here? 0. Negative 2 times 0. 0. Slope is 0. Okay? In fact, if we think about it right here, what will the slopes be all along this part of our curve? The slopes are all going to be what? Positive. What are all the x values along this part of the curve? Negative times a negative, positive slopes. All these slopes are going to be positive, right? What are all the x values going to be along here? All these x values are positive, and what are the slopes going to be? Negative. Positive x values times a negative number, negative slopes. All these slopes will be negative. Okay? So there's a lot going on there, a lot of analysis to be done simply knowing this formula for the slope of a function. So when we find the derivative like this, we're actually finding a formula for the slope. This is a formula that describes the slope of your function at any given point. All you need is the x value at that point where you want to find the slope. You plug the x value in, it spits out what the slope is going to be at that point of your function. Okay? Yeah.
Is it possible to have like negative 2x plus 1?
Yeah.
Okay.
Yes. Yes. As a slope, you're saying?
Like is that a formula?
As your derivative. You can have a derivative that's negative 2x plus 1. Absolutely. Yep. So there will be a few homework problems dealing with this tonight. Okay, I think just like 3 maybe or something like that. Okay, So take a look at those, I'll say, see how you feel about them. Won't be due till Monday. But that's just a little taste of calculus right there. Just a little taste.